Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 28, Organic Chemistry 1. Today we will continue on chapter 7, Alkyl Halides, Nucleophilic Substitution and Elimination Reactions. Organosodium reagents. When ethereal solution of alkyl halide Rx, where X, Cl, Br, is treated with sodium, coupling reaction takes place, forming RR. We call this reaction Wurtz reaction. There are two possible mechanisms, ionic mechanism and free radical mechanism. In the ionic mechanism, the sodium donates the odd electron of the outer shell to X, forming radical anion and sodium cation. The radical anion homolytic fission give radical R and anion halide. The radical alkyl group gets again electron from another sodium to form R minus sodium plus alkyl sodium. Now the alkyl sodium has R negatively charged, while Rx starting with alkyl halide we have R partially positive. So R minus will attack nucleophilic attack SN2 mechanism, will attack on the R partially soluble of alkyl halide, while getting the X halide out, forming RR and sodium halide. In the free radical, once the R radical is formed, another R radical combine together to form RR. It's highly useful in forming smaller cyclic hydrocarbons. So starting with 1-bromo 3-chloro cyclopropane, sodium dioxane as a medium and heat up, we get the bicyclo 1,1,0 butane. So if we just look at if the radical is formed here and radical is formed in here, okay, then you combine them to form a new sigma bond. When we have this one for dibromobutane in sodium and xylene, it forms cyclobutane. Again, radical here or ionic, whatever, okay, the mechanism, and radical and radical here, you form another sigma bond. If you have such compound, when we have here CH2Br, two molecules linked together in the presence of sodium dioxane at minus 78 degrees Celsius, and again we form a new bond. If you take this compound, treat it with sodium and tetrahydrofurane and tetraphenyl ethylene as a catalyst, at minus 78 we get another sigma bond, and we combine these two molecules together to get this species. Wurtz reaction is useful also in R, X, and R prime, X prime in the presence of sodium in the ether. See, R and R prime combine to form 50%. But R could combine two molecules of it together, in this case 21%, dimerize this species. And again, we find that this one combined to itself to form dimer in 29%. Here, we would like to get R prime, but we get byproduct RR and R prime. Carbenes and carbenoids. Alpha elimination, when chloroform is treated with an alkoxide base such as potassium tertiary butoxide, a small amount of its conjugate base anion is formed. This anion can lose a chloride ion to give a neutral species called dichloromethylene. This is carbene. So, treated chloroform with tertiary butoxide, here we have proton transfer to form the anion. The anion lose Cl- to form dichloromethylene, carbene. Okay? Since the carbon as H and Cl alpha, we call it alpha elimination, elimination of HCl from H and Cl on the same carbon. Before, what we took in E1 and E2, we call it beta elimination. Beta elimination, hydrogen and Cl on adjacent carbons. The presence of carbene is clearly there when we reacted with alkene. Like here, we start with chloroform, potassium tertiary butoxide, and 2-methyl-prop-1-ene. What we got? We got 1,1-dichloro, 2,2-dimethyl cyclopropane. Okay? So the carbene inserted between the alkene carbons. Okay? So two new bonds are formed in the place of the pi bond. So what happened here? The carbene has MTP orbit and has a lone pair on the sp2 orbital. Here, the two electrons of the carbene are forming a new bond, sigma bond, and the two electron of pi bond goes to the MTP forming another sigma bond. So it's cyclopropane. Stereospecific reaction. The reaction of carbene with alkene is stereospecific, which means that you start with different stereoisomeric starting material, like here we have here cis and trans 2-butene. The cis give cis dimethyl cyclopropane, whereas the trans gave the trans dimethyl cyclopropane. So in the first case, 2R3S11 dichloro 2,3 dimethyl cyclopropane is the product, whereas in the trans isomer 2R 3R 1,1 dichloro 2,3 dimethyl cyclopropane is the product. Simmons-Smith reaction. The reaction is typically conducted using diiodomethane in combination with metallic zinc and copper. It's zinc-copper couple alloy. The iodomethyl zinc iodide reacts with the alkane to give cyclopropane. Starting with cyclohexene, diiodomethane zinc copper couple led to the formation of bicyclo 4,1,0 heptane bicyclic system, where we create here the cyclopropane. Diiodomethane reacts with zinc to form iodomethyl zinc iodide. The 2 electrons here move to the CH2 forming the anion, and zinc iodide will be a positive cation. Here we call it alpha halocarbonine, moving the iodide out with its negative charge, so it will be iodide CH2, that's the methylene or carbene-like, because the carbene is not free carbene, it is coordinated to the zinc, and since it reacts like carbene, we call it carbenoid. Reaction of this coordinated methylene with alkene double bond give cyclopropane. Because they show carbene-like reactivity, alpha-halo organometallic compounds are sometimes called carbenoid. A carbenoid is a reagent that is not free carbene but has carbene-like reactivity. Getting to now preparation of alkyl halides from alkane via free radical halogenation. We have covered that earlier in lecture 18. If we have alkane, the carbon hydrogen can be replaced by carbon halogen in the presence of X2 and light. Also, if we have allylic hydrogen, we can replace it by bromine using Br2 and light, but for effective allylic bromination, a large concentration of bromine must be avoided, because bromine can also add to the double bond. We get to that later on in studying chemistry of alkene. We use N-bromosuccinimide, is often used as the bromine source in free radical bromination because it combines with HBr side product to regenerate a constant low concentration of bromine. No additional bromine is needed then, because most sample of N-bromosuccinimide contains traces of Br to initiate the reaction. So to start with, N-bromosuccinimide always have these traces of bromine. So N-bromosuccinimide with HBr, it gives bromine at low concentration, since the HBr will form as a byproduct during the reaction. It reacts with N-bromosuccinimide. So we have start with the trace of bromine light to give Br radical. Br radical reacts with the allylic hydrogens here to create this radical plus HBr. So each step of this will create HBr. This HBr is the one we are using to create Br2. So once we have anyway the radical, allylic radical, which can delocalize on two carbons with Br2 again to give the carbon bromine bond and Br radical, the step which we call propagation step. This is the initiation step and this is a propagation. These two are the propagation step. From alcohols via nucleophilic substitution, reaction with HX. We have here carbon OH. OH is bad leaving group. But when we reacted with HBr, first step is proton transfer to form the oxonium ion. Now we have a good leaving group. Water is good leaving group, right? So the Br minus will attack, here is primary carbon, and since the primary carbon, this will be SN2 mechanism to form the alkyl bromide and water. You can apply here HBr, could be HCl or H iodide. In case of having tertiary alcohol with HBr, form Br here, but in this reaction start with proton transfer and then forming the oxonium ion, which dissociate again to form the carbocation, tertiary carbocation. Tertiary carbocation reacts with the Br minus to form the alkyl halide in SN1 mechanism. Again, HCl and HI can be used as reagent. And the reaction is SN1 mechanism. Reaction of alcohol with thionyl chloride. The lone pair of oxygen from alcohol attack on sulfur, kicking the Cl out, forming oxonium. Deprotonation will lead to the formation of alkyl chlorosulfide. Now, the next step of reaction may occur by either two mechanisms depending on the reaction condition. If a base such as pyridine is present to neutralize the HCl generated in the steps leading to the alkyl chlorosulfide, an SN2 reaction occurs with inversion of configuration. Here is alkyl chlorosulfide. Cl will attack on this carbon, kicking the oxygen out to form oxygen sulfur double bond, and Cl will be out. Now this is SN2, and as you can see clearly that inversion did occur during this reaction. It's coming, Cl is coming from the back, leaving group is out. Here is going to form a double bond and Cl is out. SN2 mechanism. In dioxane, as solvent, the substitution reaction occurs with retention of configuration. The alkyl chlorosulfide undergoes heterolytic cleavage of its CO bond to give a pair of oppositely charged ions. Oxygen will carry the negative charge and the carbon will carry the positive charge. These ions, a carbocation and the chlorosulfide anion, remain together as an ion pair. Dioxane solvent solvates the carbocation on the side opposite of the chlorosulfide. The ion pair reacts by transfer of chloride ion to the same face of the carbocation as the original CO bond. This process, called internal return, and the mechanism is called SNI, where the I refer to internal. Reaction with phosphorus halide. Alcohol will react with phosphorus halides, BX3 or BX5, to form the alkyl halide with inversion in chirality. Starting, for example, with S-butan-2-ol, the lone pair will attack on the phosphorus, kicking bromide ion out. Now it's forming oxonium, very good leaving grouping here. Br will come from the back, and this group is leaving, forming the R2-bromobutane inversion with inversion, the reaction with inversion, so it is SN2 mechanism. More synthetic approaches to alkyl halide will be covered in alkenes and alkynes chapters. See you in the coming lecture. Bye bye.